Okay, so today we start the last chapter in this course, which is entitled Partial Differential Equations. So basically this is the well-known name. Usually students refer to this course by partial differential equations. However, this is only the last chapter of the course. So what do we mean by partial differential equations? Going back to Engineering Mathematics 1, the prerequisite of this course. So in that course, we solved differential equations, and in that course, we dealt with ordinary differential equations. So we had ordinary differential equations, we solved them, we learned all the techniques used to solve these equations. What did we mean by an ordinary differential equation? We mean differential equations like, these are like the most common equations, the constant coefficients equations, or maybe the Cauchy Euler equations. Of course, they could be linear, not homogeneous, but this is just a reminder of the ordinary differential equations. So now, in this course, we're doing partial differential equations. So what's the difference between ordinary? So when we say ordinary or partial, what does that refer to? So first of all, a partial differential equation, so we'll use PDE for partial differential equations. A PDE is an equation containing partial derivatives. So basically, it is a differential equation. It is a differential equation, but instead of having ordinary derivatives, primes, we will have partial derivatives. For example, let's say partial u with respect to x plus partial u with respect to t equals 0. This is a partial differential equation. Why? Because in this equation, we implicitly understand that we're dealing with a function u, which is a function of x and t. When you differentiate it with respect to x, partially differentiated with respect to x, plus partially differentiated with respect to t, you get 0. This is an equation with partial derivatives, so it is a partial differential equation. Of course, the partial derivatives could be of any order, exactly like the ordinary. So for example, it could be something like this. This is again a partial differential equation. So that's it. This is the meaning of the partial differential equation. Now, what is our, in this course, what is our goal? So what is it that we want to learn in this chapter? So our goal, in fact, in this chapter is to solve, like the ordinary differential equations, the whole course in ordinary differential equations was about solving differential equations. And now we're doing the same thing. So basically now our goal is to solve PDEs. That's it. In fact, the other goal, but that we will not do it in this course due to the time limitations, the other main goal is modeling. So although solving partial differential equations is an extremely important topic by itself, the more important topic is modeling. So what do we mean by modeling? Although we're not doing it in this course, but from time to time, we will remind you of the meaning of modeling and where to refer if you want to see some modeling problems. So when we say modeling, we mean, in fact, to move from a word problem to a math problem. So you have a word problem, we have some paragraphs describing a certain problem, then you want to write this paragraph mathematically. This transformation is called modeling. And from modeling, it seems that differential equations and partial differential equations are like they could be the most important topics related to modeling. Because derivatives and partial derivatives, so together we just call them derivatives, derivatives, they result from changing quantities, and in our world everything is changing. So as long as you're describing something changing, we expect to have derivatives, whether they are ordinary derivatives or partial derivatives. And that's the reason why partial differential equations and ordinary differential equations are very related to modeling. A simple example for modeling, Remember in Physics 1, you did Newton's law of motions, for example, Newton's law of motions. All those equations are based on the basic knowledge that the acceleration basically is the second derivative of the position. So if the acceleration, for example, is constant, so if dw prime equals a, this is a differential equation. This is an ordinary differential equation. So basically you start with a physical problem with where you have some motion. Based on the knowledge that the second derivative of the position is the acceleration, you can derive some laws of motions. For example, if you integrate this equation with respect to t, of course, this gives you d prime equals at plus a constant. But what is d prime? The derivative of the position is the velocity. So basically you're saying that the velocity is the acceleration times the time plus c. But then what is c? If you try to find c, if you substitute t as 0, you get v of 0 equals c. So basically c is the velocity at time 0, which is usually called v0. That's the initial velocity. So basically from this, we find that the velocity is at plus v naught. So knowing that the acceleration is the second derivative of the position leads to this important law of motion. The velocity at any time can be found once you know the acceleration and the initial velocity. So this is kind of a very simple, this is like the simplest modeling problem we can present. Now on a higher scale, every motion, everything that's changing, every quantity that's changing, it can be modeled somehow using differential equations. That's, for example, we have Newton's law for cooling, and this is reduced to a differential equation that detectives can use to find the time of death. This is especially used in crimes. We will see in this course the wave equation as an application, as a modeling example of using partial differential equations. We will see heat equation and Laplace equation. All these equations will be seen in this course. We'll solve them. However, for the modeling, I will refer you to the proper textbook to see how these equations are derived. They are very, very basic, but we don't have time to go over them. Okay, so this is the main goal for this chapter. After modeling, we're not doing it, we will be solving partial differential equations. So how to solve partial differential equations? Of course, this is not an easy topic. In general, partial differential equations are very tough to deal with. As we did in ordinary differential equations, we will learn some techniques. In ordinary differential equations, we did some techniques. We did like the first order differential equations. Then we did the second with constant coefficients, the homogeneous part, the linear part, the Cauchy Euler. Then we solved equations using Laplace. We did some techniques. However, in real life problems, many ordinary differential equations cannot be solved exactly. So we use series solutions, for example, to find approximate solutions. And the same for partial differential equations. Many of the partial differential equations that result in real life cannot be solved exactly, and we need to use some approximate solutions to find some estimations. And these days we have computer softwares that can help find these approximate solutions. Of course, for us, we will deal like in the first method, the separation of variables. We will do it in details. Then we will go over Fourier transform and Laplace transform to solve partial differential equations. But before going there, just to mention some very easy concepts that are very related to what we did in differential equations, and they are expected to be the same in partial differential equations. So for example, if you have a partial differential equations, what do we mean by the order? So when we say the order of a partial differential equation, that means the highest order of a derivative. So it's the highest order of partial derivatives. So for example, if you have this partial differential equation, what is the order of this partial differential equation? The order is 1. We don't say 2, although we have a derivative with respect to x and a derivative with respect to t, but the highest derivative is 1. So this is, we don't have a second derivative, for example. So this is the order of the partial differential equation. For example, if we have the second derivative with respect to x, minus the second derivative with respect to t plus the third derivative twice with respect to x once with respect to t equals 0, for example. In this case, this term here gives us the order, because here we have the highest derivative, which is 3, and the order of this differential equation is 3. So this is the meaning, very simple concept. This is the meaning of the order of a partial differential equation, similar to the order of an ordinary differential equation. Then what do we mean by, like one of the common words or phrases in ordinary differential equation was linear equation, right? So what do we mean by a linear partial differential equation? In fact, it is a partial differential equation. It is a partial differential equation that is linear in the dependent variable. So what do you mean by the dependent variable? That's the function that depends on the other variables. For example, in these two examples here, in these two differential equations, the x and t are the independent variables, and u depends on them. We look at u as a function of x and t. That's the dependent variable. So when do we say that the partial differential equation is linear? We say it's linear if it's linear in the dependent variable and its derivatives. Of course, now we're dealing with partial derivatives. So for example, you look at u. This is linear. U squared is not linear. For example, plus whatever you write then, this is equal to x, for example. This is not a linear partial differential equation. Why is it not linear? Because from the first term, u squared, this is not a linear term in the dependent variable u. So this is not a linear differential equation. For example, if you differentiate u with respect to x minus u with respect to t, that's equal to x squared. Is this linear? Now when we look at the x squared is not a linear term. But that's not how we distinguish linear partial differential equations. Linearity in differential equations depends on linearity of the dependent variable. So you look at u and its derivatives. These are the u terms. Are they linear? Yes. So for us, this is a linear partial differential equation. For example, if you take the partial derivative with respect to x multiplied with the partial derivative with respect to u equals, for example, sine x. Is this a linear differential equation? Sine x again, sine x here on the right is not linear, but that doesn't mean anything because linearity depends on the u. So this term in u is linear. However, this term in u is not linear. The derivatives are multiplied together. This is not allowed when we talk about linear equations. So this is not a linear partial differential equation. So this is the meaning of linear. So again, linearity depends on u and its derivatives. They're not allowed to be non-linear. Then the other concept that's common in dealing with differential and partial differential equations is homogeneous. So what do we mean by a homogeneous partial differential equation? It is exactly like a homogeneous ordinary differential equation. So basically, a homogeneous, and usually when we talk about homogeneous, by the way, homogeneous differential equations, we talk about homogeneous and linear at the same time. So homogeneity is related to linear equations. So a homogeneous linear partial differential equation is in fact a linear partial differential equation, a linear PDE, whose terms all containing u or one of its derivatives. Of course, what do we mean by the u? I mean the dependent variable. So what do we mean by the terms? They all have u or one of the derivatives. For example, so we're talking about linear, fine. So you write a linear partial differential equation. So if you look at this, yes, this is linear so far. The first term contains u, the second term contains u, the third term contains u, equals 0. So if you look at all terms, all of them contain u. So this is a homogeneous equation. This is a homogeneous equation. For example, if you take u sub x, so this is containing u, plus u sub x, this is the second derivative of u, it's containing u, plus tan x equals 0. This is non-homogeneous. Why is it non-homogeneous? Because in this case you have a term that is tan x. Tan x, this term does not contain any of u or its derivatives. So this is non-homogeneous. So this is how we distinguish homogeneous equations from non-homogeneous. All terms have to contain the u or one of its derivatives. That's it. Okay. So now how do we solve? This is like the easy introduction to partial differential equations. But the question remains how to solve partial differential equations. This is the big topic for us. Let's, for example, see a very simple example. Let's find a function u, just to explain some of the ideas. So you are given that u is a function of x and t. We want to find this function such that satisfies the differential equation partial u with respect to x plus u equals 0. So this is one of the simplest, if not the simplest, partial differential equation that we can see. So you have a function that depends on two variables, x and t, and this function, if you differentiate with respect to x, so the derivative with respect to t has nothing to do with our differential equation. So how do we solve such equation? So in this example, so again, we don't have u sub t. So we can in fact ignore the existence of t. So in this equation, it's like you don't have a t in this equation. So basically, aside here, I will be looking at the differential equation u prime plus u equals 0. And what do we mean by u prime? This is just aside, okay? So I'm looking at u as a function of x. Okay, it is a function of x and t. But again, the derivative with respect to t did not interfere with our equation. So basically, I can ignore it for just a little. Then we see what happens. So if you look at this equation and you solve it, this is a constant coefficients equation, right? So it has a characteristic equation that's lambda plus 1 equals 0. So lambda is -1, and the u is e to the negative x. Of course, x, not t, because the u prime now represents the derivative with respect to x. So this is the u, right? But remember, in differential equations, this is not the general solution. This is one of the solutions. The general solution is a c. It's a constant. It is a constant times e to the minus x. So if you have a function of one variable x that satisfies u prime plus u equals 0, that function must have this form, a constant times e to the minus x. Now, in our example, we have a derivative with respect to x. We have partial u with respect to x plus u equals 0. So for a function to satisfy this equation, it has to be a constant. So now what is my solution, u of x t equals? It has to be a constant times e to the minus x. But now what is the constant? The constant could be anything in terms of t. So this is the role of t in this example, because u depends on two variables, x and t. So a constant with respect to x could be anything in terms of t. T squared is a constant with respect to x. So this is, in fact, yes, this is the solution to this equation in this example. Again, this is like a very simple case when you have all the derivatives. So we can write this as a remark. So if a partial differential equation contains, or let's change the statement, sorry. So if all derivatives in a partial differential equation are with respect to one variable, so like our example, we have the partial derivative with respect to x, we don't see the partial derivative with respect to t. In this case, if all derivatives are with respect to one variable, then we can treat the PDE, in fact, we can treat it as an ordinary differential equation with constants. So then the constants as functions in terms of the other variables. So for example, to explain this, to better explain this, let's find the function u that depends again on x, y, and t, but that satisfies the second derivative with respect to x minus u equals 0. So again, in this example, we have a partial derivative. We have a function that depends on many variables, x, y, t. But the partial derivatives are only with respect to x. So in this case, you can look at this as u double prime. If you don't like the u, by the way, you can change it just to avoid any confusion, because the u depends on x, y, t. You can use anything. For example, w double prime minus w equals 0. And the w being a function in terms of x, because these are my derivatives. So in this case, this is with constant coefficients again. It has a characteristic equation. So the lambda is a plus minus 1, and the w is a constant, e to the x, plus another constant, e to the minus x. Fine? Now, after doing this, so for me, this is just a side. I do this as an intermediate step to write my solution. Then, what is my solution u? The u has to be a function of x, y, t. It is this. It is a constant times e to the x plus another constant times e to the minus x. But this time, this is our remark, the constants, we deal them as functions in terms of the other variables. So basically, what is C1? It could be any quantity in terms of the other variables that are y and t. And the same for this. So for example, if you choose the coefficient of e to the x as y or t or y times t, as long as it is something in terms of y and t, this will be your solution. These are like the easy scenarios in partial differential equations where you have simple examples, derivatives with respect to one variable. However, in general, this is not the case. So basically, we need now to go to the first rigorous method to solve partial differential equations, and that is separation of variables. So separation of variables, this is the first rigorous method to solve partial differential equations. We will see its efficiency. We will see why it's called by this name, separation of variables. And we will see when to use this method. It cannot be applied all the time. We will see. In some cases, we can't apply this method. We need to do it other way. So what do we mean by separation of variables? Before starting separation of variables, I think we need to go back a little to ordinary differential equations. We are trying to connect everything together so you have one full picture in your mind. So in ordinary differential equations, in that course, after doing the first order differential equations, we started the second order differential equations. Then we started the constant coefficients equation, the Cauchy Euler equations, the reduction of order, the series solutions, right? We did all of these. We did all of these. Of course, in the middle, we did Laplace, but Laplace is something else. We'll see it later. Even in partial differential equations, we will see Laplace and how to use it to solve partial differential equations. So, in constant coefficients equations, we started by saying let y equal e to the lambda x, and from that we had a characteristic equation. If you go back to the constant coefficients, you have a constant coefficients equation. You assume that your solution has a certain form. Then from that you find the characteristic equation. Even in Cauchy Euler equations, you start by assuming that your solution has a certain form. So you start by saying, okay, let y equal x to the r. From that you have what's called the Indicial Equation. Even in the reduction of order, after knowing y1, you assume that u2 is u y1, then you try to find u. You have some formulas to find u. In series solutions, you start by saying let y equal the sum from 0 to infinity a and x to the n. So what's common among all of these forms is that you have a differential equation. You always start by assuming a certain form for the solution, right? In all of them, you start by saying, okay, let y equal this. But it could happen that this y does not work. For example, if you have a Cauchy Euler equation and you try to solve it, for example, if you have x squared y double prime plus xy prime minus y equals 0. This is a Cauchy Euler equation. if you start and say, okay, let me solve this by letting y equal e to the lambda x, you could say that. You can start with it. But if you try, this will not work. Try it. This will not work for sure. So in Cauchy Euler equations, what works is y equals x to the r. That works, yes. And you can do the computations. But if you assume any other form, it will not work. So we need to be very careful. So assuming random forms does not work. We need to be very careful about choosing our solution form. So again, what's common among all these red equations is that you start by assuming the solution to have a certain form. Now this is still the idea of separation of variables. So the idea of separation of variables, you have a partial differential equation. So the idea of separation of variables is that to solve a partial differential equation for a function, for example, imagine you a function of two variables x and t, we assume, so it goes with the same theme as in differential equations, you assume the solution to have a certain form. But in this case, the form is a little bit more complicated. Separation of variables, this is the name of the method. You assume that you can separate the variables. So you say, okay, let's assume that after finding the solution, okay, we're not able to find the solution yet, but we assume that after finding the solution, we can separate the variables. What do we mean by we assume this? So in some cases, for example, if you have a function that's x squared times t, it is a function in terms of x times a function in terms of t. So the variables are separated. This is what's meant by f of x times g of t. But for example, if you have x squared plus t, then this thing cannot be written as a function of x times a function of t. So if the solution has this form, there is no way you obtain it using this method by assuming that u has the form f of x g of t. So of course, this method will be very limited to certain examples, yes, but it's very common. And let's say for the important examples, the wave equation, the heat equation, the Laplace equation, this method works very well. We will see. Okay, so in this method, again, we start by assuming that the solution has this form f of x times g of t. Of course, now the question is, how do we tell? How do we tell if we can solve our equation using this method or not? If we start by assuming f of x times g of t, then when can we decide if this is correct or not? We will see from the first example. So let's solve a simple example on this. Separation of variables. Then the real example will start with the wave equation we will do in a next video. So for example, let's use separation of variables to solve the very simple equation partial u with respect to x equals partial u with respect to t. Of course, we assume in this case, if nothing is given, we assume that the function is in terms of two variables x and t. So we are trying to find a function u in terms of x and t that satisfies this equation. Now the idea of separation of variables, we start by assuming that the solution has this form. And then basically what we want is, we want to find f of x and g of t. So once you find f of x and g of t, you multiply them and you get your solution. But how do we find f of x and g of t? So basically you start with this assumption and you plug it back into the equation. The equation is partial u with respect to x equals partial u with respect to t. So basically you differentiate u with respect to x, you differentiate it with respect to t. When you differentiate this u with respect to x, you need to remember that t is a constant with respect to x. So when you differentiate, basically you differentiate f, but the g is kept as a constant. And the same when you differentiate u with respect to t, but this time f of x is a constant, and you just differentiate the g with respect to t. So what is your equation? So the equation becomes, now my equation is this: partial u with respect to x equals partial u with respect to t. After finding the derivatives, you just substitute. The partial derivative with respect to x is f prime times g. So I'm not writing f of x, g of t. We understand that implicitly. equals the partial derivative with respect to t, it is f times g prime. So the idea, this is kind of an ordinary differential equation. It's a strange ordinary differential equation. It's strange because it has two functions, but it is an ordinary differential equation. It has ordinary derivatives. So the idea, the first idea in separation of variables is that you start with a partial differential equation, but then you reach ordinary differential equations. But is it an ordinary differential equation? Let's see. So let's say this is kind of the first step in solving using separation of variables. The second step, and this is the other reason for the name. So we call the method separation of variables for two reasons. The first reason is that you assume u is separated, f of x times g of t. But the second reason is you try, after substituting into the equation, you try to separate f from g. So what do you mean by separate f from g? You look at your equation. So this is your resulting equation. And you say, okay, can I separate this equation, everything in terms of f in one side, everything in terms of g in the other side? Yes, we can. So for example here, you can say f prime over f equals g prime over g. So in this case, you separated f from g. Now, this is the step. In this step, this is where you can decide if you can solve using separation of variables or not. So if you can't separate f from g, this method does not work. So if you have any partial differential equation and you say, okay, I want to solve it using the method of separation of variables, do it, start with it. And then once you start, this is like the first step, so you're not wasting a lot of time. So when you start, you reach this step, you say, okay, can I separate f from g? You can, yes, you can't, no. This is where things become clear. But what does this mean? So now the other idea, so we have f prime over f equals g prime over g. So what's next? How to find? Remember, what we are trying to find is f and g at the same time. And once you find them, you multiply them to find the u. So how do we find f and g from this step? Now the other idea here is this thing. If you look at the left side, the function f is a function in terms of x. If you look at the right side, the function g is a function of t. So in the left side, you have a function in terms of x, f. If you differentiate it, the derivative is still in terms of x, right? So f prime over f in the left is still in terms of x. So basically the idea, this side here is completely in terms of x. This side here is completely in terms of t. So what happens is that you are searching for f and g such that the left side in terms of x is always equal to the right side in terms of t. For example, just to make this idea clear, if someone says, okay, let's say x equals t, so this is a quantity in terms of x, this is a quantity in terms of t. Are they equal all the time? They're not. Okay, if x and t are equal, for example, if you say x1, t1, they are equal, yes. But what about if x is 1 and t is 10? Remember, when you deal with functions of two variables like this, the x and t are independent of each other. So the x can be any value, the t can be any value. They don't depend on each other. So you can't say x equals t. Okay? If you say x squared equals t squared, again, this is true only in very special cases, but in general, this is not true. So basically, we are looking for two sides, one of them in terms of x, one of them in terms of t, which are always equal regardless of the values of t and x. They must be equal. So if you try to write any quantities in terms of x and t to have this true, it won't be easy. The only way for this to be true, and this is the main idea in the whole solution. So here we need to clarify this. Since the left-hand side is in terms of x and the right-hand side is in terms of t, the only way for this to be true, something in terms of t equals something in terms of x all the time, we must have a constant. This is the only way. k such that f prime over f equals g prime over g equals k. So the only way for two quantities, one in terms of t, one in terms of x, to be equal all the time is that this quantity has to be a constant. So at this stage we say, okay, so there is a constant such that f prime over f equals g prime over g. What is this constant? We still don't know. And do we have enough information to find the k, this constant? We will have in other examples, but not in this preliminary example. So this is equal to k. What does it mean? This means f prime over f equals k and g prime over g equals k. But if you rearrange the terms, this is f prime minus kf equals 0 and g prime minus kg equals 0. And the nice thing is this is an ordinary differential equation. This is an ordinary differential equation. So basically you can look at the separation of variables as you start with a partial differential equation. You start with one partial differential equation, you apply the method of separation of variables, you get many ordinary differential equations. In this example, we started with one partial differential equation. Remember, this was our example. Partial u with respect to x equals partial u with respect to t. This is one partial differential equation. We started with it. We applied the method of separation of variables. We obtained two, at this stage here, we obtained two ordinary differential equations. This is the idea. In some cases, if you have three variables, you will have three differential equations and so on. So once you reach this step here, after that, what happens is you solve. So now we solve f prime minus kf equals 0 and g prime minus kg equals 0. Now these are very simple ordinary differential equations. We solve them, we find f and g, we multiply them. So what is the solution for the first equation? These are with constant coefficients. So the characteristic equation here is lambda minus k equals 0, which means lambda equals k, and the same for the other one, lambda equals k. Right? These are with constant coefficients. So basically, what is the function f? It is e to the kx. What is the function k? G, sorry. It's e to the kt. Remember, f is in terms of x, g is in terms of t, but we have constants, of course. So we have a constant here, we have a constant here. So after finding, and that's it by the way, after finding f and g, so what is the solution to your equation? You multiply, remember this is the method of separation of variables. So you just take f, the function f, which is c1 e to the kx, you multiply it with c2, you collect the c's into one c like this, and this is your solution. However, what is the k? The k could be any real number. So basically this is not one solution, if you agree. So because when k is 1, this is a solution, when k is 2. So these represent infinitely many solutions. Then how do we deal with these infinitely many solutions? Again, this is like the first example to show you the idea, just the main idea of separation of variables. But how do we deal with these cases and these constants? This will be done in details in the first real example, which is the wave equation. So I hope this example is clear to explain just the basic idea of separation of variables, and we continue in the next video with the wave equation.